Hi, I wanted to give you an explanation to essential question number 2, version 3 in the fall of 2011. So here's the sequence we're looking at, and by now you may have gotten used to the idea that when you're dealing with linear gradients, they always have to come from time period 0, and when they're not, they have to be like supported or pushed down by linear gradient sequence. So what I'm going to be doing for this problem is thinking about it as a couple of different chunks. The first chunk goes from time period 0 all the way out here to time period 7. And the second chunk is going to start at time period 8 and go out to time period 12. The way I'm thinking about it is that this early time period, see we got this linear gradient looking part over here in periods 4, 5, 6, and 7. Well, that has to start someplace, and it's got to start up here at 10. So we've got a constant series that's 10 high. And this little chunk over here, which is a linear gradient that kind of falls off from it. The chunk that goes from 8 to 12 is similar, except backwards. What we're looking at here is a constant series that's 5 high that goes from 8, 9, 10, 11, and 12. And what sits on top of it is this little linear gradient series. So this is another one of those ones that's going to have 4 parts that is associated with it. So let's go ahead and start getting our present worth out here again. So we'll start with our present worth. And first this constant series that's 10 high, looking for P given that we know A, I, and we'll figure out what the N is in a bit. Leave room to time shift. That's a 1 plus I. Then the linear gradient series, which looks like it goes down by 1 each time. So we'll put a minus 1. Looking for P, given that we know G is the I. We'll figure out the N and the time shift. That's 1 plus I. And then this linear gradient series right here. And so this one is 5 high. Looking for P, given that we know A. Here's the I. And we'll figure out what the N is and all the little time shifts are. And then this linear gradient sequence, this one that goes up by 1 each time. Looking for P, given that we know G, that's a slash. Here's the I. We'll figure out the N and also the shift that has to take place. So let's work out what all the N's and shifts are. First, let's deal with this big constant series of 10s that we have up here. There's 1, 2, 3, 4, 5, 6, 7, 8 of these. Remember, all you really need to do is count the number of non-zero elements. That's all I do. And then we got to get the shifting to work out right. Now, what's odd about this one is a constant series shouldn't have anything at time period 0, so we know that we have to shift this around a bit. And if you put a minus 1 right there, what you'll see is this denominator basically gathers all its value on time period minus 1, and the denominator shifts it from minus 1 to 0. Nice check, 8 plus minus 1 is 7, and that's the last time you see that constant series. Now the linear gradient, count this one, 1, 2, 3, 4 of them. So there, 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 and there. You add 1 for the pot because that's the way linear gradients work. It makes for a more attractive equation. This one, let's use the time shifting rule. We got to get it so this is last period is in time period 9, and so a 4 does the trick because 5 and 4 is equal to 9. And that should handle this whole left-hand side. The right-hand side over here, we've got a constant series that's 1, 2, 3, 4, 5 long. It also happens to be 5 tall. That's just a coincidence. And what this thing does is the numerator here dumps all the value onto time period 7. So if we put a time period 7 right there, it should shift the value back to 0. And if you want to double check, 5 plus 7 is equal to 12, which is the last time you see the constant series. And the final chunk is this linear gradient series. You see how it jumps up by 1 each time over on the right? Well, we see that once, twice, 3 times, 4 times. So we add 1 for the pot over here to get up to 5. And then we can use the same kind of addition rule to find out that it shifts by 7. And we should be okay. We should have the present worth of the sequence. Anyway, here's one of the ways of writing out the present value of this in factor notation for essential question 2, version 3 in the fall of 2011.